Here are solutions to homework set number 10 for ECE 463-663 Modern Control. This homework set looks at finding feedback gains using optimal control or LQG methods. That's linear quadratic Gaussian. Now LQG is pretty much the same as pole placement, just another tool. Is you set up a cost function, find the optimal feedback gains, basically the optimal pole locations given your cost function. I don't like the word optimal because it's optimal for an arbitrary cost function, but it's a tool. It's another way to find feedback gains. So we're going to do that for 3 different systems. The first one is a cart and pendulum system. That corresponds to this response. So here we've got a cart and pendulum. I want to go from point A to point B, get it to be stable, have a nice step response, basically find the full state feedback gains that does that. So how do you do that? Well, the first approach is to set up the dynamics. So here's the dynamics of the cart and pendulum system back from homework set number 4. Just to make it easier, I'm going to specify the desired dynamics. I want the settling time to be 8 seconds, meaning the real part of the pole is at 0.5, minus 0.5, 5% overshoot, that tells you the damping angle, tells the complex part. Basically, I want to put the closed loop poles at minus 0.5 plus J.52. I'm then going to use optimal control to find your feedback gains Kx. And to do that, what I'm going to do is I'm going to weight the output. Let's go over to MATLAB. I'm going to sit there and play with the gains. This is the Q matrix where the output is Y, C transpose C. This is the Q matrix for Y prime, CA transpose CA. I'll then use those as knobs. I can adjust the gains on position and velocity. If I just do position, here's my desired response in red. There's the actual response in blue. It's a little bit sluggish. To speed it up, crank up the gain. And with LQR, you don't do subtleties. You don't do 1, 1.1, 1.2. It's like 1, 10, 100. Make a big change. 100 is too fast. 10 is not bad. Let me try 30. Maybe too much. 20. Okay, let's add some friction now to get that hump down. Let's try 10 friction. Okay, that's pretty good. Once you're happy with the response, I found my feedback gains. So here the weightings I chose were 20 and 10. There's nothing magical about 20 and 10. That's just knobs I played with to get my desired response. When I'm done, I wound up with feedback gains, Kx. If I go over to MATLAB, wherever MATLAB is, right here. There's my feedback gain. I placed the closed loop poles somewhere. So that's where I put the closed loop poles. If I did pole placement, use the same pole location, I'd get the same answer for Kx. This is not a pole location I would guess normally. You know, these two poles kind of make sense. That's your dominant pole that tells you the settling time. It interacts a little bit with these poles because they're not 10 times faster. Apparently this is slightly, well, this net combination gives you this step response. So it's called optimal control, but again, it's optimal for an arbitrary cost function. When you try it, eventually, each time I do it, I get slightly different answers. Here's what I did when I tried it on the homework solutions. The weighting of 15 on position, 0 on velocity, gives you this response. The resulting closed loop poles are here. Back from pole placement, that's where I put the poles. And the feedback gains are similar, maybe a little bit smaller using using LQR. That tends to be a feature of LQR. You tend to get smaller gains, and small gains are good. Small gains mean you need less energy, smaller input, it's less sensitive to modeling errors. All good things. So maybe these gains are better. I like pole placement because we've got complete control over the response. I like LQR because you tend to get smaller gains. Which one you use is really up to you. It's a matter of taste. It's a tool. If the tool works for you, use it. So that's problem 1. Problem 2 says, what happens if you have 2 inputs? Now this is where pole placement had a problem. With the techniques we're using, Bhaskara doesn't really work for 2 inputs. With LQR, it doesn't care. If I have 2 inputs, I just define my A matrix, same as before. I define my B matrix. I now have 2 entries in the B matrix. I can find the feedback gains using LQR. I'm going to wind up with a 2x4 matrix, 8 feedback gains, because I have 2 inputs, 4 states. To set the DC gain. DC gain, I've got a problem. If I do C A minus BKX inverse B, it's a 1x2 matrix. I can't really invert a 1x2 matrix. So to make it a 1x1 matrix, I'm going to assume the input for force is the same as the input on torque. So my input is B times KR times reference. I'm going to pick KR in this form. When I do that, I wind up with a 1x1 matrix. So now I can find the DC gain. And again, the DC gain comes from right here. There's KR. I'm going to guess the DC gain, or KR is 1, 1. Find the DC gain. This is now a 1x1 matrix. I can invert a 1x1 matrix. And that gives me my constant to make the DC gain 1. To find your feedback gains, again, what you do is to kind of guess again. So here's my desired response, the red line, same as before. My feedback gains, I'm going to weight position, the output y, and y dot. Try it with the weighting of 1, 0. So here's my desired response in red, actual response in blue, a little bit sluggish. So crank up the gain on y. Not damn lucky. Okay, pretty good. Let's try 9. That looks actually really, really good. So at that point, I'm basically done. My system has the desired response. Actually, that was pretty easy. Or 10. When you're done, if I look at my feedback gains, I now have a 2x4 matrix. I have 8 feedback gains to play with. The first one is times force. The second one is times torque. My KR matrix is 2.52, 2.52. I assume they're both the same. If I apply 1 Newton of force, I apply 1 Newton meter of torque. If I look at the closed loop poles, they're somewhere. This is where pole placement doesn't really give you the same answer. Pole placement can't handle more degrees of freedom than constraints. LQR doesn't mind. So in this case, I'd actually say LQR superior. I can use both inputs, and these aren't just simple multiples of each other. Each gain is completely independent, whatever it takes to optimize your cost function. Third one is, let's try this one more time. Third problem is find the feedback gains for ball and beam system. So here what I'm doing, I'm applying a torque to the beam that gets it to rotate. Gravity then pulls the ball right. I want to get the ball to go to 1. And I think it was 8 seconds, 5% overshoot. Come up with a feedback control that does that, but now use LQR techniques. So again, the technique is the same, given the A matrix, given the B matrix. Set up your cost function. I want to minimize A, B, Q, and R. R, I'm just going to set to 1, and play with Q. In MATLAB, I can do that. I'm going to sit there and play with the weightings on Q. So if Q is, there's position, angle, velocity, angular velocity. Let's weight position. Yeah, that looks really bad. Crank up the gain on position. And maybe it's getting better. With oscillations, that typically means you need to weight velocity. So let's add some weighting on the velocity of the beam, or velocity of the ball. I think that got worse. Maybe. And these are just knobs. Let's look at this gain. Suppose I change the weighting on beam velocity. Okay, that didn't seem to help. Let's change the weighting on beam angle. Didn't seem to help. Let's go with this one. So this is the velocity that I'm weighting. Again, I'm just playing with the gains, trying to get a good response. Okay, too much. Well, that's not bad. And really what you're doing, oops, too much. Try 2000. It's kind of a trial and error. I've got knobs to play with, just the knobs until the response looks good. When you're done, I have my optimal gain Q, or my weighting Q. For that Q, I can find the optimal feedback gains. And just by playing around with it, you eventually get something. Eventually wound up with 100,000, 1,000. Each time I try, it gets slightly different. But that gives you this response, which is not too bad. When you're done, I've got the feedback gains. And then pick KR to make the DC gain 1, same as before. When all said and done, I place the poles somewhere. So that's the optimal place to put the poles for that arbitrary cost function. With pole placement, here's where I put the poles. And kind of notice they're similar-ish. Pole placement's nice. I've got complete control over it. The feedback gains, LQR versus pole placement, are actually not all that different. So which one's better? In this case, I'd kind of say it's a wash. But that's homework set number 10. Really what you're doing is you're using LQR as a tool. It's one way to find feedback gains. It's a little bit different. With LQR, what you're really doing is playing with the gains until the step response looks good. And it's nice because with pole placement, I just have too many degrees of freedom. With this one, I just have a couple degrees of freedom, play with them, and kind of see what's happening. It's behaving fairly well. I can get pretty good responses with just a few iterations. But again, it's just a tool to find feedback gains with the advantage that it's always stable, the gains tend to be small, and it works for multiple inputs. That's homework set number 10 for 463-6663 Modern Control.